Alright, in this lesson we'll be talking about exponential functions and some of the applications for exponential functions in the real world. Exponential functions are anything with a variable in the exponent. So this right here classifies this as an exponential function. So we have a variable in the exponent. It can have other stuff up in the exponent as well, but the main thing is that it has to have a variable. It's variable in the exponent. The base, in this case the 2, doesn't matter quite as much. That could be anything. And you'll see a couple of different examples today, actually. So to start off, we're going to just figure out what this looks like. We are going to plug in some points on our table and plot some points. So because this has an exponent in the variable, variable in the exponent, plugging things in will just look like taking 2 to the power of whatever x we're plugging in. So you might remember that 2 to the 0 power, in fact anything to the 0 power, is just 1. So we'll have the point 0, 1, and then 2 to the first power is 2. 2 to the second power, 2 times 2, which makes 4. And then 2 to the third power is 3 2's multiplied together, which makes 8. The reason I did the positive numbers first is because there's a specific pattern that I want you to notice as we start moving into the negatives here. 2 to the negative 1, remember that negative exponents are the inverse of repeated multiplication, which means that negative exponents actually repeatedly divide. So it moves things to the denominator of the fraction. So 2 to the negative first power is actually 1 over 2 to the first power, which is just 1/2. And then 2 to the negative second power is 1 over 2 squared, which is 4, 1/4. And then 2 to the negative third power is 1 over 2 to the third power, which is 1/8. So you might notice that there's a pattern going on here, that these two look alike, and so do these two, and so do these two. This pattern makes a lot of plugging stuff into exponential functions easier. If you plug in like 2 to the negative third power into a calculator, it will give you a decimal. I recommend fractions because of this pattern. Otherwise, with decimals, you can't see what's happening here. But this pattern will continue as the powers of 2 get bigger on the positive end. You'll also get like 1 over 16, and then 1 over 32, and then 1 over 64, and then 1 over 128. You're just multiplying that denominator by 2 each time, the same way that you would be going the positive direction. So we sort of have matching numbers going positive and negative. Another thing to mention is that as the numbers get more and more negative, the output, the y values, are getting smaller and smaller, because each time essentially we're dividing by another 2, so we're dividing the previous one in half each time. But what's interesting about that is that when you divide something in half over and over and over again forever, you'll never get to 0. You will get like infinitely close to 0. You'll get so small, but you'll never get to 0. Which gives this function what we call an asymptote, and we'll talk about that more when we graph it. So I'm just going to start plotting these points. I have a 0, 1 point, and then hopefully you have these written down, and then a 1, 2 point, and then a 2, 4 point, and then a 3, 8 point, and then going in the negative direction I have 1/2, and then a 4th, and then an 8th, and then I run out of my table. But the next one would be 1/32, and 1/16, and then 1/32. So our graph looks something like, let's see if I can make this, nope, I'll start from this end. Yikes. Still not my best. I don't know. I'm not drawing graphs well today. We all have our days, right? So we get this sort of nice curved graph if you draw it correctly. This is what people talk about when they talk about exponential growth. The reason that they're referring to this kind of growth on this kind of graph, that it grows very quickly, very fast. And back to that thing that I mentioned called the asymptote. This function will never touch 0, never touch or cross 0. So it gives it, this function has sort of a line that it never crosses, and that's what we call an asymptote. It's kind of a funny word that sounds rude, but it's actually not, unless you want to use it that way, that's great. But the asymptote is sort of just like a line that function will never cross, but it gets infinitely close to. And knowing where the asymptote, especially for graphing exponential functions, knowing where that is super helpful for graphing them, and you'll see why later when we do this. But that asymptote is, it's just a line that graph gets super close to, but never crosses. Clearly we don't want to make a whole table every time that we graph these, so what's most important to graphing exponential functions is knowing where, sort of making this mini table, plugging in -1, 0, and 1. These are pretty easy to plug in exponential functions because 0 is always 1, unless you have like a vertical shift happening, or an add or subtract after. 3 to the first power is 3, and then 3 to the -1 power is 1 over 3. So just to clarify, I'm now graphing 3 to the x power, not 2 to the x power, which is why my numbers changed. So those 3 points will give you sort of a pretty good idea of what this function looks like, especially knowing that the asymptote is still at 0. Makes it a lot easier to graph than making a whole table every time. This asymptote, in fact, never changes unless you have a vertical shift. So this is always at 0 unless vertical shift. So going back to our last lesson, a vertical shift is whenever you have added or subtracted something outside of the function, and we'll see an example of this actually. On your homework also, there's a question that asks you for the equation of the asymptote. Equations of asymptotes are y equals something, so this one specifically is y equals 0, so is that one up here. This is also a y equals 0 asymptote. And it stays at y equals 0 unless you shift the whole graph up or down some by adding or subtracting a number on the outside. So that would look like +2 or something on the outside of the function. So yeah, we can make that sort of mini table with -1, 0, and 1 in it, and then graph it using the knowledge of where the asymptote is. So let's turn the page. We're going to graph a couple of exponential functions here. First we have 4 to the x power. This one does not have any vertical shifts, so I'm just going to prematurely kind of draw the asymptote because I know it's going to be at 0 still, y equals 0 specifically. And then I'm going to make a mini table with -1, 0, and 1. So 4 to the 0 power is 1, 4 to the first power is 4, 4 to the -1 power is 1/4. So graphing that, it looks like 0, 1, 1, 4, and then a 4th. And there's my exponential function. Next we have 2 to the x power plus 1. So I want us to notice here that this does have a vertical shift. So we move the whole function up 1. So the asymptote is going to move up 1 from where its original position is. So I'm going to graph my asymptote at y equals 1 now, because we've moved the whole thing up 1. And then I will make my mini table here with -1, 0, and 1. These are like slightly harder to plug in just because we have to add 1 after, but that's not too bad. So 0 is 2 to the 0 power plus 1, which is 1 plus 1, which is 2. 2 to the first power plus 1 is 2 plus 1, which is 3. And then 2 to the negative first power is 1/2. Plus 1 is 1.5. So at -1 I'll go up 1.5. And 0 I'll go 1, 2. And then 1 I'll go up 3. Which makes this lovely curve. There we are. So that's what it looks like when we have shifted something up, the exponential function up 1. That's a vertical shift of +1. One more. Before we even make a table for this one, I want us to notice that there is a negative multiplied on the outside of the function. So using our knowledge from last time, we know that that should flip the function vertically. So before we even graph it, we know to expect something that looks like this, because normally it looks like that. So flipped vertically, it will look something like that turned down exponential function. We also know that the asymptote has not changed because there's no vertical shift. There's a vertical flip, but there's no vertical shift. So it's still at 0. So knowing that, I'm going to make a little table here with -1, 0, and 1. For 0, going somewhere. For 0, we have -3 to the 0 power, which is -1. And then -3 to the first power is -3. And then -3 to the -1 power is -1/3. So each of those I can graph. 3, which gives us what we predicted. This turned down exponential function. Yeah. So now that we have graphed a couple of those functions, we're going to talk about some applications for exponential functions. And it turns out there are a lot. Exponential growth and decay is something that happens in nature. We use exponential growth and decay to model populations. Specifically, usually it's like bacteria populations, things that grow really quickly. Isotope decay, radioactive isotope decay, and there was another example I was thinking of. Nope, it left me. That's okay. There's also the application of money in a savings account, and we'll talk more about interest in the second application here. But this is a sort of a general growth and decay formula. I'm going to say now, before I forget to say it later, that the math space, the homework, often uses equations that are just slightly different than the ones that I'm giving you. So my recommendation is to check the hint button before you plug everything into an equation, because there's a good chance that it might be a little bit different. The good thing is that they are really similar, so that you'll be able to interpret like what goes where in the formula, because they're so similar, but using the wrong formula will get you the wrong answer, so just be careful about that. The formula can change depending on what specific situation you're looking at, and also like what kind of results you want. So anyway, just double check that. So this formula has a P in it. It's a P because it stands for principal, but it's also the starting amount. Principal is a word we use mostly with money, but it does mean how much you started with. Then we have the T, which is time, and then we have the R, which is the rate. the rate of growth or decay, depending on what kind of problem you're doing. The rate specifically needs to be in decimal form. Many times they will give you a rate as a percentage, so like 45% is a rate. To change that into a decimal, you just have to move the decimal place 2 places to the left. So 45% is 0.45. 4% is 0.04. So just make sure you're moving the decimal place 2 times. This formula doesn't super work if you are plugging in percentages. They need to be in a rate, in a decimal. Last we have e, which is not in fact a variable. It's standing in place of a specific number. This number is something that shows up in nature a lot, and so we've sort of given it its own name. It's very much like pi, except for pi we used a Greek letter, and e is just a, one we have in English. So anyhow, so it's very much like pi. Also like pi, it's a decimal that never ends or repeats, so it's kind of a cool, it's cool. Anyway, so E helps us to measure growth and decay in nature, which is like what this formula is specifically looking at. So you'd never have to plug in E. I will add to that calculators will have an e to the x button. On the ones that we have in school and the ones that are loaded on your Chromebook, it's actually, I should fix that, it's actually above the button with LN on it. It's like a little blue e to the x, and you'll have to use the second button to get there. Most calculators will have an e to the x button though, because it's a very common thing. So e to the x will just give you an e to the power of, and then you plug in the power, which is exactly what we want. So that hopefully will be useful to you. So you don't have to know what e is, you just need to find the button. The first problem is Dr. Simon is trying to model the growth of a certain kind of bacteria. She knows it grows at a rate of 25% an hour, and she began with 100 bacteria. Model this growth using the exponential growth function. So we have the starting amount of 100 bacteria, the growth rate of 25% an hour. In this problem, we do not have a time. What we're trying to do here is just model the growth of this bacteria, not get a specific answer. Like, we don't know how long she's wanting. Like, she's not asking us, like, oh, how many bacteria will there be after 3 hours? She just wants a formula that you can plug any time into and get the number of bacteria that exist then, which is great. So we don't have to plug anything in this one. Into a calculator specifically. We do have to replace P with 100 because that's the original amount. And then we have E, which is not really a variable. Then a rate, so in 0.25 is what I need to put there, times T, which I don't have. So that's my rate. Here's my starting amount. And that's as far as we can go on that problem because we do not have a time. So that's it. Number 2, Amanda takes 400 milligrams of ibuprofen. The amount of medicine in her system decreases at a rate of 29% each hour. How much will be in her system 4 hours after she takes it? So again, we have A equals P times E to the RT. And let's highlight some things here. 400 milligrams is the starting amount. 29% is the rate. We'll talk about that in a minute. And then 4 hours is how much time. So this one we do have all the pieces of our formula. Start with 400, e to the, okay, now let's talk about the rate. So it's saying it decreases at a rate of 29% an hour. So I would invite you to pause me for a second and think about how you might make this so that it's decreasing instead of increasing. This formula that we just wrote over here, the bacteria is increasing. It's a population increase, so we have a positive rate. A negative will make this a decreasing formula. So I have to make this a negative 0.29 so that it's decreasing at that rate instead of increasing. And then lastly, we have 4 as the amount of hours. This is something you can plug into a calculator and get the answer for it. I think I have it written down. So plug it into a calculator. Again, maybe pause me so that you have time to plug it in. If you plug it in correctly, you should get 125.39 milligrams, which makes sense. I encourage you to always make sure that your answers make sense. If she starts with 400 milligrams of ibuprofen and 4 hours later she has like 10,000 milligrams of ibuprofen in her system, that seems bad, right? Just make sure that your answers make sense, and you should be good. Okay, next we have this interest formula. This is specifically about compound interest. Essentially what compound interest is, this is what most banks, the system that most banks employ. They, essentially it just means that if you have money in a savings account, like I have $100, and then I'm paid like $2 of interest, then the next time they assess interest, they will assess the interest on $102. So they include what they already paid you in interest into the like money that you have. Anyway, so it makes sense for sure, especially if you're like in a savings account or if you're borrowing money. Compound interest is usually what's happening. So this has a lot of the same variables, except for it doesn't have an E in there. This is, I'm gonna label this principal now because we are talking about money now, but it is the same thing. So principal is just the amount that you start with. This is the interest rate specifically. Interest rate as a decimal. And then we have, T is time, specifically time in years for this one. And then we have this other variable, N. N is the number of times that interest is assessed per year. So this one usually they tell you with a word instead of a number. They'll use the words like biannually, which means twice a year, or quarterly, which means 4 times a year, or monthly, which means 12 times a year. This is just the number of times interest is assessed per year. And that's our formula. So we have Chelsea here. Chelsea borrows $125 from her parents at an annual interest rate of 15%. How much will she owe if she doesn't return the money for 5 years? So we have the principal amount of $125. 5 years is how long. The interest rate is 15%. And then we have this added information of annual, which means that it happens once a year. Interest is assessed. Okay, so we have, it's jumpy today. A equals the principal amount, which is 125, times parentheses 1 plus the rate at 0.15 over n, which is 1, we decided, to the 1 times 5. Before we go ahead and plug this into a calculator, I'm going to just simplify a little because dividing by 1 and multiplying by 1 don't do anything, so that's the same thing as this. And then you can plug that into a calculator. Just make sure that you're using parentheses to make sure the calculator is understanding what you're saying. But you should get something like $251.42. That's how much she will owe her parents if she borrows for 5 years. Last one here, Felicia is trying to remember how much she originally invested. She knows her account currently has $456.50 in it, and her interest rate is 4% biannually. She originally invested 7 years ago. How much did she start with? So we have biannually, which means twice a year. The interest rate is 4%. Time is 7 years, and $456.50 is how much she originally invested. So I want to, actually no, that's not. It is not how much she originally invested, that's how much she has now. And she's actually trying to figure out how much she originally invested. So this problem is going to be a little bit different because we actually have the A in our formula, we have this one, but not the P. So we have what the amount is currently and not what it was originally. So let's just write that out here. I'm going to start with the formula so we are clear on what we're replacing with what. The A is going to be $456.50. The P we're not sure, so we're going to leave it as a P. And then the rate is 0.04, careful with that conversion. And biannually is twice, so 2, and then 2 times 7 up there. And before we plug anything in, I'm just going to simplify. 1 plus, oops, missed the 1 there, 1 plus 0.02, and then up here is 14. 2 times 7 is 14. Now what we can do is we can plug this into a calculator to see what value that gets us. And I encourage you to pause so you have enough time to plug it in. But that number should give you 1.32-ish. And then we still have 456 on this side. In order to solve this, we have to just do a tiny bit of algebra by dividing by 1.32 on both sides so that that goes away. And then we will just have P on that side, and then 456.50 divided by 1.32 gives you $345.83. So just checking to make sure that makes sense. It doesn't make sense that she started with $345 in her account and then 7 years later she has 456. To me, that makes sense. Make sure that you're not getting like a bigger number. Hopefully, you shouldn't lose money. Anyway. So that makes sense to me, and that is our solution. So that's all I have for you.